In exercise 1 to 4, determine if the system has a non-trivial solution. Try to use as few row operations as possible. If the system has a non-trivial solution, that means the system should have at least one free variable. So now here we have a system of linear equation. We need to know if the system has a free variable. That means the system has a non-trivial solution. So let us write the matrix for number 1. Then we do the row operation to see if there is a free variable. So after doing row operation, this is the basic matrix or the first matrix. Then we do row operation. We get the final. The final one, which is this one. 2 minus 5 8 0, 0 minus 12 9 0, and then 0 0 0. So it's same here. This matrix has 2 pivot position, which is here 2 minus 12. There is no pivot in the third row, so that's mean x3 is a free variable, so the function or the system has a non-trivial solution. So since x3 is a free variable, then the system has a non-trivial solution. So because of the free variable, the system has a non-trivial solution. In the same way, we do number 3, not 2. So 3 also we have 2 equation with 3 unknown. So from here it is clear we cannot have more than 2 basic variable, because here we have only 2 rows. There is no more pivot than 2. So from here it is clear that this matrix, if it is consistent, for sure it has a free variable. So if we do row operation for this one, row 2 is equal to row 1 plus row 2. This will give us another matrix, which is minus 3 0 5, minus 7 here 0, then here minus 3 15 0. So now this matrix, it is clear it has 2 pivot, which is this one and this one. So it has only 2 pivot. That's meaning x3 is a free variable. So since x3 is a free variable, then that's mean the system has a non-trivial solution. As I said from the beginning, that if this system has only 2 equations with 3 unknowns. If the system consistent, so it should have at most 2 pivot position. In exercise 5 and 6, follow the method of example 1 and 2 to write the solution set of the given homogeneous system in parametric vector form. So here we have a linear system. We need to find the solution. Then we need to write this solution as a parametric form. So first we need to write the matrix, then we need to solve this system. So here we have, this is our matrix. Then after row operation, we get the final result of this matrix. So from here, it is clear that x1 is equal 5x3, x2 is equal minus 2x3. Well, x3 is a free variable, which is x3. Now to write it as parametric form, so from here x is equal x1, x2, x3, which is equal. We see here x x1 have x3, x2 have also x3, so here we have x3, so we'll take x3 as a common factor. Now the coefficient of x3 for x1 is 5, the coefficient of x3 in x2 is -2, and here the coefficient of x3 is 1. So this is a parametric form of the solution set of the matrix in exercise number 5. In exercise 7 to 12, we need to describe all the solutions of Ax is equal to 0 in parametric vector form, where A is row equivalent to the given matrix. So here we start by 7. We have this matrix. We need to do one row operation, so we can write here row 1 is equal -3, row 2 plus row 1. We get the matrix here. The new matrix is 1, 0, 9, -8, then 0, and the second row is 0, 1, -4, 5, 0. So now we have two pivots because we have only two rows, so we cannot have more than two pivots. To write the solution set in parametric form, we know we have x1, x2, x3, x4. So we write it here, x1, then x2, x3, x4. So this will give us x1 is equal -9, x3 plus 8, x4. x2 is equal 4, x3 minus 5x4. x3 and x4 are free variable. So we see here the two common variable are x2, x3 and x4. So from here we can take x3 as a common factor plus also x4 as a common factor. And then we take the coefficient of x3 for all these 4. So from here the coefficient of x3 is -9, then this one is 4, then this one is 1, this one is 0. x4, here we have 8, then this one is -5, this one is 0, this one is 1. So this is the parametric form of the solution of the matrix A. Similarly, we do the same for number 11. So we start by this matrix, then we do one row operation, we get this matrix, another row operation, we get this matrix. From here we have x1, x2, x3, 4, 5, 6. We have a pivot in the first row. We have also a pivot in the second row, and the third row. So from here it is clear that we have 3 free variable and 3 basic variable. So to write the solution as a parametric form, first we write x is equal. So from here we have x1, we have x2, x3, x4, x5 and x6. So this will give us, so x1 is equal 4x2 minus 5x6. So 4x2 minus 5x6. We can write here 1, 2, 3, 4, 5, 6. Then x2 is equal, so since here there is no x2, that's mean and no x2 is free variable. For x3 is this one, it is equal to x6. Now x4 is here, there is no pivot for x4, so that's mean x4 is a free variable. x5 is this one, so x5 is equal for x6. And x6 is here, there is no pivot for this one, so it is x6. Now to write this one as a parametric form, we see here we have x2, x4 and x6. So we have x2, plus x4 plus x6. So the factors of the coefficient of x2 is 4, 1, 0, 4, 1, 0, then 0, 0, 0. The coefficient of x4 is 0, 0, 0, then 1, 0, 0. Then the coefficient of x6 minus 5, 0, 1, then 0, 4, 1. So this is parametric form of the solution of exercise number 11. In exercise 13, suppose the solution set of a certain system of linear equations can be described as x1 is equal 5 plus 4x3, x2 is equal minus 2 minus 7x3. With x3 free, use vectors to describe this set as a line in R3. So for this one, if we write x is equal x1, x2, x3. So it is given that in x1 is equal 5 plus 4x3, x2 is equal minus 2 minus 7x3, and x3 is a free variable. If we write this one as a parametric form, so here we have 5, the constant, minus 2, then 0, plus x3 as a free variable. Here we have 4, minus 7, and 1. So to describe this one as a line in R3, the solution set, it is clear, is a line through this vector which is parallel to this vector. So we can write here the solution set is a line through 5 minus 2, 0, parallel to the vector 4 minus 7, 1. And if you want to write this one as P plus TV, where T is any scalar, so this will be the solution set is a line through B parallel to the vector V. In exercise 15, follow the method of example 3 to describe the solutions of the following system in parametric vector form. Also, give a geometric description of the solution set and compare it to that in exercise 5. So here we have a linear system. We need to write it as a matrix. Then we need to do row operation to find what is the solution. So here our matrix is, this is the first matrix. Then after doing row operations, we get the last one is this 4. So now from here, we want to write the x or the solution. So x is equal x1, x2, x3, because we have we have only 3 unknown. So x1 is equal 5x3 minus 2. x2 is equal minus 2x3 plus 1. x3 is equal, there is no x3 here, so x3 is a free variable. Now to write this one as a parametric or as a vector form, so here if we take first the constant, so the constants here minus 2, 1, 0, plus x3 is a free variable, so here we have 5 minus 2, 1. So to describe this one as geometrically, it is the solution set is a line through minus 2, 1, 0 parallel to 5 minus 2, 1. So we can write here the solution set is the line through minus 2, 1, 0 parallel to the vector 5 minus 2 1. In 17, describe and compare the solution sets of x1 plus 9x2 minus 4x3 is equal to 0 and x1 plus 9x2 minus 4x3 is equal minus 2. If we say this one is A and this one is B. So now for A, we have x1 plus 9x2 minus 4x3 is equal to 0. So we have three variables. We can write it as x1 is equal minus 9x2 plus 4x3. Now x is equal x1, x2, x3. So we know that x1 is minus 9, x2 plus 4, x3. x2 is a free variable, x3 is also a free variable. So this will give us x2 multiplied by minus 910 plus x3, we take the coefficient of x3 from here, 401. So from here we see that the solution set is the solution set of this set is a plane through the origin spanned by the vector minus 910 and 401. So the solution set is a plane through the origin spanned by spanned by the vector minus 910 and 401. Now let us do the same thing for B. We have x1 plus 9x2 minus 4x3 is equal minus 2. So from here x1 is equal minus 9x2 plus 4x3 minus 2. So from here our x is equal x1, x2, x3. So this will give us minus 9x2 plus 4x3 minus 2. This one is x2 and x3 also free. So now this will give us, from here the common is x2 and x3. So x2, the vector of x2 is minus 9, then 10 plus, for the x3 we have 401. Then since we have the constant here, we have to add it. So this one is minus 200. So the solution set is here. It is a plane through the vector minus 200 and spanned by these two vectors. So here the solution set is a plane through the vector minus 200 parallel to the solution set of Ax is equal to 0, which is this one. Of Ax is equal to 0. Because we know that if we have Ax is equal to B, the solution, if the solution exists, it will be parallel to the solution set of Ax is equal to 0 and it is through the vector B. So this is just a solution of Ax is equal to 0. This is solution for Ax is equal to 0. That's why here we write it, it is parallel to the solution set of Ax is equal to 0, and it is through this vector. In exercise 19 and 20, find the parametric equation of the line through A parallel to B. We know that if we have a solution or parametric equation of the line through A parallel to B, it should be in the form A plus TB, where T is a scalar, or where T is in R. So now we have this one, so our X is equal, so X is equal X1 and X2, because we have only just two vectors. So this one will give us X1 is equal minus 2 minus 5t, and then 0 plus 3t. This is because our A is minus 2 and 0, our B is minus 5 and 3. So X1 will be minus 2 minus 5t, X2 will be 0 plus 3t. Or we can write it like X is equal X1, which is equal minus 2 minus 5t, and X2 is equal 0 plus 3t, or just you can write it 3t without 0. So now for 21, find a parametric equation of the line M through B and Q. So this is the line M through B and Q. Hint, M is parallel to the vector Q minus B. See the figure below. So we have this is B and this is Q. We know that the line through M and parallel to Q minus B is written by, so here we have 21. This can be written, or X is equal P plus T multiplied by Q minus B, where T is a scalar. So this is a line through B parallel to Q minus B. This is the equation of this form. You can write also X is equal Q plus T multiplied by Q minus B, because B and Q are in the same line. So either you choose B or you choose Q, it does not matter. So now we have X is equal P plus T multiplied by Q minus B. So this will give us, what is our B is 2 minus 5, then plus T multiplied by Q minus B, so minus 3 minus 2, this will give us minus 5, 1 minus minus 5, this will give us 6. So this is a parametric equation of the line M through B and Q and parallel to the vector Q minus B. In exercise 23 and 24, mark each statement true or false. Justify each answer. So the first one, A homogeneous equation is always consistent. This one should be true, because we know that if, so this one A is true, because Ax is equal to 0 always has a solution when x is equal to 0, which is a trivial solution. When x is equal to 0. Then B, the equation Ax is equal to 0 gives an explicit description of its solution set. This one we said it is from the textbook. B, false, it gives us implicit because we write it as x1 is in the form of x2 and x3 and so on. So this one false, it is give us implicit description. Now for C, the homogeneous equation Ax is equal to 0 has the trivial solution if and only if the equation has at least one free variable. This one is false because we said it has a non-trivial solution. not trivial solution. So this one is non-trivial solution. For D, the equation x is equal b plus tv describe a line through V parallel to B. This one is false because it describes a line through here, a line through P parallel to V, not vice versa. A line through B which is parallel to V. Now E, the solution set of Ax is equal B is the set of all vectors of the form W is equal P plus VH, where VH is any solution of the equation Ax is equal to 0. This is from theorem 6, which is the last theorem, but here it does not say that Ax is equal to B has to be consistent. So this one is false. Ax is equal to B should be consistent. For some B or for some given B. Because the solution set could be an empty, so that's why here we need to say that the solution should be exist. Now let us do 24. If x is a non-trivial solution of Ax is equal to 0, then every entry in x is non-zero. We said that for the non-trivial solution, at least one entry to be non-zero. So this one is false. At least one entry is non-zero. Then B, the equation x is equal x2u plus x3v with x2 and x3 free, and neither u nor v multiple of the other describe a plane through the origin. This one is true because it says that the equation of x2u plus x3v, so this is a linear combination of these two vectors. None of them is multiple of the other. That means they construct a plane through the origin. So this one is true. So B, true. Now for C, the equation Ax is equal B is homogeneous if the zero vector is a solution. We know that the homogeneous system Ax is equal to 0. But here it said Ax is equal B is homogeneous if the zero vector is a solution. If the zero vector is a solution, so if Ax is equal to B, and we know that the zero vector is a solution, so that's mean A multiplied by 0, this will give us always 0 because we multiplied by 0. So this will give us a homogeneous system, so this one should be true. Now the effect of adding B to a vector is to move the vector in a direction parallel to B. So if we have a vector and we add this vector to B, does that mean we move the vector in a direction parallel to B? Here yes, because if we, according to the paragraph in the parametric form, we said that if we add, for example, b plus tv, we move the vector, translate the vector b in the direction parallel to the vector tv. Similarly here, if we add b to a vector, that means we move the vector in a direction parallel to b. So this one D should be true. Then part E, the solution set of Ax is equal to B is obtained by translating the solution set of Ax is equal to 0. Here it should be first Ax is equal to B should be consist first. Then we can say that the solution is translating the solution set of Ax is equal to 0. So here this one is false. Ax is equal to b should be consistent. Now for 25, prove the second part of theorem 6. Let W be any solution of Ax is equal B and define VH is equal W minus B. Show that VH is a solution of Ax is equal to 0. This shows that every solution of Ax is equal B has the form W is equal B plus VH, with B a particular solution of Ax is equal B and VH a solution of Ax is equal to 0. So for this one we are given that W is a solution of Ax is equal B. And also we given that B is a particle solution of Ax is equal B. That means AP is equal B. Also it is given that VH is equal W minus B. We want to show that VH is a solution of Ax is equal to 0. That means we need to show that AVH is equal to 0. So let us first write AVH. What is AVH? So if we take the left hand side, we want to reach to 0. So that means AVH, it is equal A. What is VH? It is given from here. It is W minus B. So now if we distribute A, so this will give us AW minus AB. But we know that W is a solution of Ax is equal B. That means AW should be equal B minus AB. It is given it is equal to B. So this will give us 0, which is the right hand side. So VH satisfy Ax is equal to 0. Thus every solution of Ax is equal B has the form W is equal B plus VH. So we can write here, so VH satisfies Ax is equal to 0. Thus every solution of Ax is equal B has the form W is equal B plus VH. In 26, suppose Ax is equal B has a solution. Explain why the solution is unique precisely when Ax is equal to 0 has only the trivial solution. We know that the relation between the solution of Ax is equal to B and Ax is equal to 0 is the solution of Ax is equal to B is the same as the solution of Ax is equal to 0 translated by B vectors. So if now Ax is equal to B has a unique solution, that means just only Ax is equal to 0 also has a unique solution. Because if Ax is equal to 0 has many solutions, that means will affect the solution of Ax is equal to B because it's dependent on the solution of Ax is equal to 0. So whenever the solution of Ax is equal to 0 is unique, which has only the trivial solution, the solution set of Ax is equal to B also should be unique. But in the case Ax is equal to 0 has many solutions, that means Ax is equal to B also has many solutions. So let us write this here. So if Ax is equal to B consistent, that means the solution of Ax is equal to B is obtained by translating the solution of Ax is equal to 0. So the solution set of Ax is equal to B is a single vector which is unique if and only if the solution set of Ax is equal to 0 is a single vector. When ax is equal to 0 has a single vector, the solution of this one, if and only if ax is equal to 0 has only the trivial solution. So if the ax is equal to b has a unique solution, that's mean ax is equal to 0 also has a unique, and vice versa. Because the solution of ax is equal to b depend on the solution of ax is equal 0. Now for 28, if b is not equal to 0, can the solution set of ax is equal to b be a plane through the origin? For this one, if b is not 0, can we include 0 in the set of solution ax is equal to b? This one is no, because if the solution, if the solution set of ax is equal b contain the 0, or contain the origin, that's mean إنه then 0 satisfy a0 is equal to b, because if the solution includes 0, that's mean a0 is equal to b. But here we know that, but b, it is given that b is not equal to 0, but b is not equal to 0, so we cannot include 0 in the plane since b is not equal to 0. But b is not equal to 0, which is not the case. Which give us this statement is true. Sorry, this statement false. We cannot say that the origin is in this one when b is not equal to 0. So I think here it will be enough until here. So, but b is not equal to 0. From here we conclude that this origin cannot be in the solution set whenever b is not equal 0. So in exercise 29 to 32, does the equation ax is equal to 0 have a non-trivial solution? And b, does the equation ax is equal to b have at least one solution for every possible b? So for example, here we have 29. A is a 3 by 3 matrix with 3 pivot positions. For example, if we take this matrix 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1, which has a pivot in every position. Now, if this one is 3 by 3 with 3 pivot position, we need to answer, does the equation ax is equal to 0 have a non-trivial solution? If it has a pivot in every row, so all the columns are span R3, so there is no free variable. So the first answer is no free variable. That's mean there is no non-trivial solution. Because we said that the matrix has a non-trivial solution if it has a free variable. Now b, does the equation ax is equal b have at least one solution for every possible b? Yes, because this one is consistent and it has a pivot in every row. That's mean all possible b can have a solution. All b or every possible b have a solution for this matrix. So from here, yes. Or we can write here there is no form, which is 0, 0, 0, b, because there is no form of this one. All of the rows has a pivot position. Now 30, A is a 3 by 3 matrix with 2 pivot positions. So if we have, for example, this matrix with 2 pivot positions, so if we said 1, 0, 0, then we have 0, 1, 0, and the last one is 0, 0, 0. So this matrix has 2 pivot positions. It is 3 by 3. So now let us answer A. Does the equation ax is equal to 0 have a non-trivial solution? Here, yes, because this only have 2 pivot positions. That means the third one will be may be a free variable. So this one here, yes. because we have two pivot position. So that's mean two basic variable and one free variable. That's mean there exists or there is an non-trivial solution. So let us say there exists a non-trivial solution. Now for part B, does the equation ax is equal b have at least one solution for every possible b? Here if b is the last entry of the b here, for example, if it is non-zero, that means the system is inconsistent. So the answer here is no. Not all p make the system consistent. Especially if we have when b3 is not equal to 0. Because if b3 here, we have the last column, if b3 is not equal to 0, the system is inconsistent. Now let us see 31. A is a 3 by 2 matrix with 2 pivot positions. So we have a 3 by 2, 3 rows, 2 columns, 2 pivot position. For example, if we have this one, 1, 0, then 0, 1, 0, 0. So now A, does the equation ax is equal to 0 have a non-trivial solution? We said here there is no, because no free variable. Because this one has no free variable, that means there is no trivial solution. Now B, does the equation x is equal b have at least one solution for every possible b? Also we said this one is no, especially if b3 is not equal to 0, the system inconsistent. Because if the last b here is not 0, we have the system of the form 0, 0b, which is inconsistent. Now 32, A is a 2 by 4 matrix with 2 pivot positions. So for example, if we have this one, 1, 0, 0, 1, then the rest, for example, here, whatever value. So now, does the equation ax is equal to 0 have a non-trivial solution? Here, yes, because only we have 2 pivot, that means 2 others will be free variables. So here, a yes, because we have 2 free variables. Now part B, does the equation ax is equal b have at least one solution for every possible p? This one also yes, because the system is consistent. Is consistent for any p. So this is just an example. That's, you know, if it has a trivial solution, if it does not has a free variable, and if ax is equal to b could be consistent or inconsistent. In 33, given a is equal minus 2, 7, minus 3, minus 6, 21, minus 9, find one non-trivial solution of ax is equal to 0. By inspection, hence think of the equation ax is equal to 0 written as a vector equation. We know that ax is equal to 0 can be written as, for example, since here we have 3 rows, 2 columns, that's mean null a multiplied by x1, x2, this will give us equal to 0. So our a is here minus 2, 7, minus 3. and minus 6, 21, minus 9. So we take the first entry here multiplied by the first column. So x1 multiplied by minus 2, 7 minus 3 plus x2 multiplied by the second column minus 6, 21 minus 9 is equal to 0. We need to use, or we need to take 2x, which is x1 and x2, that give us this equation to be true without solving this one. So non-zero we need to take. If we take, for example, if x1 is equal to minus 3 and x2 is equal 1, so that's give us, if x is equal, here we have x1 and x2 we said. So if x1 is equal minus 3 and x2 is equal 1, this will give us minus 3 multiplied minus 6 will be 6. 6. 6 minus 6 will be 0. Then minus 3 multiplied by 7 minus 21 plus 1 multiplied by 21, this will give us 0. Then minus 3 multiplied by minus 3 will be 9. 9 minus 9, this will give us 0. This is 0 vector, not a 0 element. So this inspection is true. So if we take x is equal minus 3, 1, we get this one is true. Also, you can take another x. For example, if you swap this one, for example, 3 minus 1, also you will get the same answer, which is this gives you 0, 0. You can choose infinitely many solutions that satisfy this product, or that give you a non-trivial solution. So for 3, 4, given a is equal 4 minus 8, 6 minus 6, 12 minus 9, find one non-trivial solution of ax is equal to 0 by inspection. So we'll do the same way we did it in 33. So we need ax is equal to 0. That means we need x multiplied by x1 multiplied by the first vector 4 minus 8, 6 plus x2 multiplied by the second vector minus 6, 12 minus 9. This should be is equal to the 0 vector. So for example, if we take x1 is equal, for example, is equal half, then x2 will be equal, so this will give us half. 4 is 2. 2 we need to add it to something which x2 multiplied by minus 6 to give us 0. For example, if we multiplied x2 will be 1 over 3. So half 4 will be 2 plus third minus 6 will be minus 2. This will give us 0. Half minus 8 will be minus 4 plus third 12, which is 4. This will give us minus 4 plus 4, 0. And this also for 6 will give us 3. This one minus 3, which give us 0. So x will be equal half 1 over 3. You can choose any x. Let's give you the result. So this is for 34. Now for 35, construct a 3 by 3 matrix which is non-zero, such that the vector 1, 1, 1 is a solution of ax is equal to 0. So for 35, we need a matrix, 3 by 3 matrix, such that this matrix, when we multiply it by 1, 1, 1, the result should be equal to 0, 0, 0. So here you can construct any matrix which is non-zero. So for example, if we take this 1, 1, then this 1, 1 minus 0, we multiply the first row with the first column, this will give us 1 minus 1, 0, and we get 0. Then if we take, for example, this one is minus 2, this one 2, for example, this one 0. So it will be minus 2 plus 2, which is 0. Then the last row we can take it 0, 0, 0. So this is just an example of a 3 by 3 matrix which is non-zero, such that the vector, when we multiply it by the vector 1, 1, 1, we get ax is equal 0. Similarly, for 36, we need to construct a 3 by 3 non-zero matrix A such that the vector 1 minus 2, 1 is a solution of Ax is equal 0. So if we multiply this matrix by 1 minus 2, 1, we should get the non-zero vector. We should get the 0 vector 0, 0, 0. But the matrix should be non-zero matrix. So here 0, 0, 0. So also here you can choose any value. So for example, if we take this one 1, 1, 1, then 1 multiplied by 1, 1, plus minus 2 plus 1, this will give us 0. For the second one, we can take this one 3, 2, 1. So 3 minus 4 plus 1 will give us 0. Now if we take, for example, this one 2, this one half, this one minus 1, so 2 minus 1, then minus 1, this will give us 0. So you can choose any matrix 3 by 3 which satisfy this equation Ax is equal 0.